Hello, and thanks everyone for coming back to the last two sessions. Hello in the back. Okay. So last two sessions here. So the first one is going to be Julian and Lucas talking about shipping a Vulkan game in 2024, which is fairly exciting. So we see more Vulkan content in this conference, but that's one of those like hard-earned lessons from doing things for real and not just talking on Twitter about it. So I'm fairly excited about this one. And we'll have time for questions at the end, so just keep your questions posted and then we get to them. Take it away, guys.
Thank you. I hope you all can hear me well. Yeah, fine. So just give you some context, and then most of the talk will be about what graphics abstraction layer we have in-house and how the Vulkan backend is implemented for that and how that Vulkan backend influenced the decisions we did to design our graphics abstraction layer and change that. This talk will not be an introduction to Vulkan, so it will be more around the middle of this schematic demonstration from the first triangle to actually having a shipped game somewhere in there, right? So, but there's lots of resources out there in the internet for the first Vulkan triangle. All right. There's a couple problems. We will talk about some of them we found on the way, but first talk a little bit about King Games. There was a talk before, but yeah, just repeat it. King Games, we are a studio, a game development studio from Frankfurt, Germany. We have around 70 people, and we shipped, I think, 38 games in the last 19 years. Most of the games are mobile games, though, so are Nintendo DS games, smaller games in the past. And you see the last 4 games we shipped before our current project. This is Lucas, and he's a senior graphics programmer in our team. And my name is Julian. I'm a technical director. So most of the bugs of the Vulkan code is actually my work, and he tries to fix them. Some history. As I said, we shipped a couple of mobile games in the past. One of them was Olympus Rising, so a mobile game we shipped on iOS Metal and on Android. And we actually shipped one of the first Android games using Vulkan back then. And it was quite a ride. Lots of drivers broken then. Basically, we had a whitelist of all the devices that worked instead of having a blacklist. So it was a couple dozen devices where we actually enabled the Vulkan backend. Everything else shipped OpenGLES. But there was a major improvement especially in CPU time on the Vulkan backend, and it allowed us to multi-thread submission and recording, which was a big benefit back then. All right, coming to the next, or the current game, the current project. Maybe you saw the talk earlier about the GI solution. So that's Enshrouded. It's an open-world action RPG with a gigantic dynamic terraformable world. You can actually play the game outside now, I think. So if you're curious, then can take a look. Yeah, and we actually shipped that game using Vulkan in our in-house engine. So this is a rough sketch about kind of the graphics stack, right? So Enshrouded on top is around 1.5 million lines of C++ code. Not exactly, but roughly. The renderer is roughly 100,000 lines of C++ code and maybe 50,000 lines of HLSL code. And then the graphics API and the Vulkan backend, and there's a couple more backends for other platforms, but the Vulkan backend is actually pretty small comparatively. It's around 11,000 lines. Just the numbers in absolute don't matter too much, but just the comparison, that's a very, very, very tiny part of the whole stack. Don't know anything about the driver, but I assume it's much bigger than everything on top of it. All right, as I guess most game developers working for games that have to ship on multiple platforms, we have our own hardware abstraction layer. And over time, like over the 38 games we shipped, that went through a couple of backends that we shipped it with. Ancient stuff like D3D9, 11, and we actually have a D3D12 backend now, OpenGLES, and a couple more esoteric APIs on other platforms. It's our abstraction, and the advantage of that is that we can evolve it. So whenever we start a new game, which has very different requirements, we can adjust the API accordingly and match it to the platforms you want to ship the game on and what you actually need it for. For Enshrouded, for example, we did a clear cut, and we basically disabled all the backends, just used Vulkan and evolved the API quite a bit to get the more modern features in. So this is basically all the concept I will be talking about that we abstract in our graphics abstraction layer. First, we talk a little bit about devices, and then frames. Don't have to read everything here, but it's basically all you need for the renderer, or what we need for the renderer. So devices first. Devices allows us to create device objects like textures, buffers, and other resources. So it's basically owning these objects and allows us to allocate and create memory, bind this memory to resources, flushes caches, has the frame abstraction that we'll talk about later, and access to an asynchronous transfer queue. So that's basically what the device is in our graphics abstraction layer. We only have one device ever. There's no multiple device things happening. All right, to actually create the device in the backend, we search for the best device. There's a couple of things we need from the device. It's called features. So first we start with, we only require Vulkan 1.2 right now. Maybe even in the future we want to switch to 1.3, but right now it's 1.2. And we search for all these features, and if these are not available, then we don't consider this device. There's a couple of extensions that we need. And then after that, we search for devices that, or we assume that devices are ordered in the priority that the user expects them to be selected, or the driver expects them to be selected. So we basically take the first one that takes all our requirements, or fulfills the requirements. There's a special hint you have to do on for NVIDIA and for AMD. You have to define these magical constants somewhere in your code to make the driver possibly select the better GPU on the laptop sometimes. Next thing we do, we try to decode, or we decode the version number. So Vulkan has an API to get the version number of the driver. This is a very cryptic format. You can decode it like that, and then you can compare to a known good version that you have tested in the UK, and then display a warning, or don't start a game, which we don't do. So we display a warning because there are problems with older drivers. So that was all the easy part. Now for something interesting, not sure who here knows about Vulkan layers. So Vulkan layers is the idea that you can inject basically code in the Vulkan API. That's very useful, I guess, for overlays or for video recording software or for other things. And oh boy, there's a lot of layers out there, and most of them are broken in our experience in some way. And there's no way for us to detect that really. So when we first shipped Enshrouded last year in the Steam Next Fest, we didn't do anything about it, and we had thousands of crashes that all looked like broken layers. So we now have code in place that actually just looks for, has a blacklist, so of all layers we detect that are known bad, and we test them internally in QA and filter out of most of them. Unfortunately, that's not the perfect solution yet. So if one of you knows a better solution to this problem, I think TinyGlade shipped a little bit more sophisticated solution, so maybe worth looking at that title, which is one of the other Vulkan titles this year. So there's a special example for OBS, because OBS shipped a broken driver in an old version, and then the uninstaller of that didn't uninstall the version. So basically, when you installed a new OBS version, it never uninstalled the broken layer, and there was no code anymore in the system to ever uninstall that layer. So it was there forever, and we explicitly filtered it out. We try to find it and ignore it. just an example. All right, so we finally got a device working. Next thing we have in our graphics abstraction layer is the concept of a frame, and it should be pretty similar, like familiar to most game developers. But we have it as an explicit thing in our graphics API. So basically, the game, these JPEG artifacts are horrible. Yeah, but the game at the beginning calls begin frame, basically, and then submit frame, when it's done recording all the commands. And from then, it goes into translating the command buffers that we wrote into Vulkan commands, submitting the frame, then GPU renders that, then we wait for that, and then we do cleanup, like the deferred deletion of objects that got deleted. So this is the lifetime of one frame, and it spans multiple time frames, right? As you say, right? We interleave multiple of these, we overlap them, because the CPU can already start with begin while the submit is running, right? So it looks like that. If you have multiple, so we have frame n, n plus 1, n plus 2, CPU, this is the CPU graphics layer, and the GPU works on this respective frame. So that means we just have a single fence, right, for each frame, wait for that, and then we know all resources that got destroyed in this frame actually not used anymore, we can just free all of them. There's quite a bit of resources that we store in there. So all the descriptor set pools, all the command buffer pools, the memory blocks for staging, dynamic memory for the constant buffers, all of these are tied to a frame, which makes it pretty simple and practical for us to work with. All right, yeah. So translation means we write a software command, so-called software command buffer first. So the actual renderer writes these commands into basically a byte buffer, right? Byte encoded. And these are pretty similar to the Vulkan commands, which just draws and setting pipelines and dispatches. And then in the backend, the Vulkan backend, we actually translate that into actual Vulkan commands. So there's multiple reasons for that. One is history, right? We used that same concept back then for OpenGL, and OpenGL doesn't allow multi-threaded submission. So we basically did that in one thread, and then the submission thread converted this command buffer into OpenGL calls. So we had it already. It's one of the reasons. The other reason is it's actually good for the instruction cache to write all these commands in place and then do translation differently, because sometimes these go deep into the driver, especially barriers. So it's good to group them together into the submission. This translation code in our game takes around 1 to 1.5 milliseconds right now for all the commands. As you see here, this pseudocode of our Vulkan backend. So at the beginning, we set the command pools. Then we have this one single Vulkan command buffer that we begin. And then we have a loop here where all our software command buffers translate each command and submit everything to a queue and queue present. So very simple. I mean, please do error checking for all of these, right? But to get the idea. All right. All right, we have this frame construct. Now we want to actually render something. The most important thing is pipelines. We actually are a pretty, I guess, untypical game. We don't have a material graph or anything. So we have a fairly small number of pipelines. And this includes everything you saw earlier with GI and everything. The only problem is the VFX system, because that's complicated. It uses some expressions, it's compiled down to HLSL and individual pipelines, which is hopefully solvable. But it's around 500 pipelines and then 8,000 for VFX. All of that is written in HLSL and compiled into SPV using DXC. So that's pretty fairly typical. And for code is fine. The only problem we had in the past and right now with multiple other platforms, the binding is very different for platform to platform. On PS5, we heard earlier this morning, we have so-called root descriptor tables, and these are very different, right? And so we create our own domain-specific tiny toy language, call it graphics pipeline configuration, which is funny because it's GPC, and Lucas will tell you a bit about that right now.
Yeah, so as Julian said, GPC is our custom, domain-specific language to declare everything that goes into graphics or compute pipelines. Earlier we had a manual approach where you would write HLSL files, put them into our asset pipeline to compile them to SPIR-V, and then load them manually in C++ code. And you also had to declare descriptor set layouts and pipeline layouts and everything you need for Vulkan in C++ as well. That became tedious to keep in sync on both sides. And as Julian mentioned, different platforms have different requirements about how bindings are specified. So we designed the GPC language to mitigate all of those problems. So we now have a single location where we declare everything that goes into pipelines, all the states, all the bindings, all the shader code. And we generate everything that we need for the different pipelines solely from that data. And we also generate a lot of C++ code to make loading those pipelines and binding resources to those pipelines as simple as possible. As an example, you can declare a descriptor set layout with a couple of resources. We generate HLSL code for Vulkan in this case, with those VK binding annotations that you can use in DXC. And we also generate a struct that you can use in C++, where all of those bindings are exposed, and you can just use regular C++ code. And there's some helper libraries that then translates those descriptors, structs, into respective Vulkan calls to bind those resources. Another very big issue we had before that was declaring C++ structs and upload them directly to the GPU to use for constant buffers or storage buffers. And the big problem for those with those was that there are padding requirements or layout requirements, and C++ aligns members of those structs differently than what the GPU uses, and the GPU uses requires different layouts for constant and storage buffers. So we solved that also by having a meta or the domain-specific language, which is very close to C++ with just some restrictions. For example, arrays aren't supported. And we also generate C++ structs from those. We generate matching HLSL structs, and we are making sure that the layout fits. And you also have to annotate these structs respectively, so you can only use a struct that's meant to be used in a storage buffer in storage buffer resources, and for constant buffers, vice versa. Oh, and push constants also. They also have different layouts occasionally. And that, with that, we had to figure out all of those layouting issues once, but we managed to solve them for the very most cases and mitigated a lot of bugs that we had earlier. So another neat things that we added to GPC, we have a couple of small features. For example, we have a no helper lines annotation. You can add that to a rasterization pipeline. And we would, with that, we check the SPIR-V instructions, whether there's any instruction in there that requires helper lanes. And with that, you can just you can put that in and make sure that your shader doesn't require any helper lanes. We had issues with wave intrinsics earlier that were operating then on helper lanes, but that was unexpected. And with that, we're just checking that, and you can be sure that there's nothing in your way. We also have an annotation that you can use our bindless descriptor set. Julian will talk about that very soon. Output pixel formats, for example, everything is one big design decision of GPC was to declare everything in our domain-specific language and generate code as required instead of parsing existing HLSL code or inventing own HLSL syntax to get required data out of that. Yeah, for example, for the output pixel formats, we use that because it's required in Vulkan, but also for PlayStation code, for example, we can generate the respective formats in the PSSL code then. Yeah, static samplers are also supported pretty easily with that. As you know, maybe in Vulkan, it's a bit weird to get those working, but with GPC, we managed to hide all that in the backend or helper code, and yeah, you can just use them and use them the same on every platform. We have limited support for generating different pipeline variants based on, for example, whether float 16 is supported by the GPU or not, and debug variants, which yeah, you can just use then as a if-def debug to add code that you would only want to ship in the debug, for debug builds. Yeah, one thing that's also supported with GPC is hot reloading, so you can just change either shader code or GPC code, and the system hot reloads those changes while the game is running, as long as it's possible. For example, when you would change the signature of your, if you would change GPC declarations that in a way that would change the pipeline layout, you can't hot reload anymore, because then you would also have to adjust the CPU code. Otherwise, yeah, bindings don't match up. And we also had crashes earlier due to that, and with that, we also negotiated those.
All right, thank you. Yeah, now we have defined all the pipelines. We have to compile them, and unfortunately, DXC is very slow. So for us, it takes 1 to 2 seconds per pipeline. We don't have that many pipelines for the general renderer, but 8,000 times 2 is a lot of seconds already. So that's one of the major limiters, I think. I would be very happy about a faster way to offline compile these shaders in any way. Because that's very limiting, especially if changing a shared header file that is used in a lot of VFX, then you have lots of minutes to wait. There's a couple of things we don't like, really. These bindings in nature are global. We much prefer a way like Metal, where you pass the bindings, basically parameters to your main function, and then have to propagate it like in normal C++ code. Because the shaders get so big that like having all available globals is limiting. Another thing we would love to have for DXC is right now we compile each stage individually, but in GPC we actually have the whole pipeline defined. So ideally we would give DXC the whole pipeline with all these stages, because then we could do cross-stage optimizations, for example, remove inputs to a pipeline or outputs when inputs are not needed from the following stages. Right. But as you all heard, right, we're adopting SPV now as the DXC internal intermediate language, so everything will be much better in a couple of years, hopefully. This actually opens up a potential for someone, if you're looking for a student project, right? I would love to have a fast HLSL to SPV compiler, right? So just as an idea, fast meaning at least 20 times faster than DXC. That would be fairly doable. Right, so we have all the pipelines compiled. Unfortunately not, right? We're not in consoles, so we still have this driver that needs to recompile everything again. Interesting question, by the way. Like, why do we spend 2 seconds optimizing this VV in the beginning, and then the driver takes another 2 seconds to optimize it for the ISA of the hardware? Can't we maybe get rid of some of these seconds somewhere, please? So for our game, like the 500 pipelines, we just compile in the initial loading screen. That's fine. The 8,000 pipelines would take too long. So what we do is, I think what a couple of games do is we let QA play the game for the first 15 minutes, list all the pipelines that are necessary, like all the torches you find at the beginning of the game, collect a list, and that these are the preloaded ones. Everything else is compiled in the background while you play the game. It's a bit unfortunate, because if you do a driver update and then start the game again in your base somewhere far away in the game, then some VFX are missing for some time. So what we do then is we boost the priority of these missing ones, because then it takes a couple of seconds only. Steam Deck is actually better, right? Because they distribute the precompiled binaries, and it's on Steam Deck we load all pipelines in the beginning. It's actually worth verifying the SPV code before you send it to the driver. We had a couple of crashes, like I think 0.1%, which we have a lot of players, so that's a lot of crashes related to probably invalid code that we gave the driver, and drivers decided to crash, which I don't blame them for that, right? So have a checksum, and you can at least handle that case then, potentially. So pipeline caches, neat idea. You can read all of that, but basically the verdict is don't use it. We shipped initially with pipeline caches. There's a lot of problems. The wins for us were minimal and very specific. They're very different on different vendors, and we turned it off basically. Because yeah, it's actually not that easy to invalidate the cache and to update that when you have new versions, and then you have to make sure that the cache doesn't grow exponentially. You have to clean that. So a lot of headache that's probably not necessary in our experience. We didn't try this new extension yet. Maybe that solves everything. I don't know. All right. So next section is about memory management. Lucas wants to take over.
Yes, memory management. Yeah, we basically identified 4 different types of memory that we allocate. Like first is static memory. This is memory that's allocated once, either for the entire runtime of the game, or like a set of memory in the main menu, and then we free that, and then also some static memory when you load into the game scene. And we have streamed memory, which is texture streaming, model data, VFX data, and we also have some SDF data. This is memory which is basically reallocated all the time, like while the game is running. We have dynamic memory. That is memory that depends on the quality settings or on the window resolution. And this is stuff that we have to allocate when either of those change. And stuff that is required for the next frame. So we, for all the temporal render targets, for example, we have to keep those around for the next frame. And the fourth type is temporary memory. This is also memory that depends on settings and resolution, but this is stuff we only need during a single frame. For example, just a temporary render target you render once into and write once from, and then you don't need it anymore. We currently restrict ourselves to 6 GB of VRAM, assuming the GPU has 6 GB of VRAM, which, leaving some space for Windows and other applications, basically leaves us with 4.8 GB of VRAM that we can actually use. We split this up into budgets for the different memory types I just mentioned. And note that this is only VRAM that we are allocating from the GPU device. There is additional Vulkan memory that we allocate from the host memory. For staging stuff, obviously. And we are also using that right now already as fallback for UI textures, because those take up a lot of memory in our game, and they're not visible that often in many cases, and just using them or letting the GPU read them via PCI Express is fine as a fallback in some cases. The streamed memory is pretty easily, you can easily budget that and rescale that, because the streaming system just uses the budget it has and it can work with any budget. So that's very easy to scale, but it obviously has to fit in the budget that we allocate. One of the main benefits with using Vulkan over what we used in Portal Knights, which was D3D11, is explicit memory management. So finally, we have control over that. We started with the excellent Vulkan memory allocator from AMD. That's great. You can just plug it in, and it works very well. But we started moving towards our own memory allocator to have more control, especially with the dynamic stuff and the temporary stuff I mentioned. yeah, it's like we have more control if we do manage the allocations ourselves because we know exactly when we need to reallocate stuff. Yeah, we are using the following memory extensions that are just listed here to try to get the memory demotion that was talked about in the earlier talk a little bit under control, but still like with limited success in our case, I would say. Yeah, it would be very nice to have some more information from the operating system about how much memory we can safely use or when memory is about to be demoted or when it was demoted to maybe find a better solution that would fit our game more to yeah, promote memory again. Yeah, basically that's what our memory management looks like. We have different memory types. This is also like relates to the memory types that are exposed by Vulkan. And yeah, we just linearly sub-allocate from memory chunks. Like sometimes there's gaps in between because resources can have different alignment requirements, but we try to pack those as tightly as possible. Yeah, the little API that we have for allocating memory looks like this. It was designed with the idea that we can very easily specify where we want to allocate memory from, or basically what kind of memory it is, be it dynamic memory, static memory, or this temporary memory. And we also started to work towards aliasing memory in a single render frame. And this is, so you can go back once? Yeah, thanks. This is a bit exposed by those memory scopes. For example, the idea is that you declare a memory scope that is basically valid for this one function call, in this example, this render volumetric fog sky. And you can basically use allocations in this scope, which correlates to this function, and once you're out of this scope or out of this function call, those things might be invalidated because other stuff was aliased on top of this memory. And this is what it looks like in the game. Like we have on top we have the static data that's allocated once. This is just a single chunk, linearly allocated. And for the temporary memory, in this case, we have two render views already. One is the main scene view, the 3D scene, and the smaller one is the 3D character view that we have in the UI. Those are aliased already over those memory chunks. When we would now rescale the window or so, those would need to be reallocated, but we're trying to reuse the existing memory chunks to lower the stress that we put on the driver to reallocate device memory blocks. Yeah, a few words about texture streaming. Yeah, we are estimating the MIP levels that we require from textures based on feedback from the GPU culling. So we are not using sampler feedback, but instead our GPU culling system, just while culling stuff, returns a minimum distance an object is from the camera. We feed that back to the CPU and compute the required texture resolutions based on that. And then try to find a good solutions to load as many textures as possible so that it still fits in the budget. Those are then, like for those, we kick off loading, and once we got the data from our resource system, we schedule an async transfer and update the Bindless descriptor once that is done.
That's where I take over now. So we have all this memory. Now we have to connect it to the shader, the pipeline, right? And we're going to use descriptor sets for that. And descriptor sets are an abstraction, and they try to solve a really hard problem because GPUs are very different, and the way the shader access or can access resources is very different. So that's a abstraction that they came up with. We in the game currently use up to 4 descriptor sets at the same time. Usually it's less than that, so that's the limit. And in a couple of slides before, we talked about this frame. So most of our descriptors is actually allocated per frame dynamically. So the Enshrouded is using a GPU-driven pipeline, so we don't have that many actual CPU-driven, like CPU spawned draw calls. So we don't have that many commands in the software command buffer in the first place. We don't have that many descriptor sets. So it kind of felt easier to just do it this way, and you don't have to deal with the lifetimes. And it's pretty fast for the small set. So I would recommend starting with that first. Just forget everything, reset the descriptor pool, and just write every descriptor set again each frame until you know you have a problem. As you saw earlier, we have the GPC compiler making sure that the C++ structs map. I wouldn't underestimate how many bugs you can solve with that. So I highly recommend something like that. Yeah, we'll talk a little bit about validation later. All right, so Bindless. We do use Bindless rendering in Vulkan because we are GPU-driven, have a GPU-driven pipeline. We kind of have to. But we only use Bindless where we have to. So there was, back then when we started the project, there was quite a bit of problems with using Bindless in and debugging tools. So we try to minimize the use of Bindless textures. Actually, you only use for basically the stream textures from materials, for SDF chunk data, which is the geometry of the game, and I think a couple other things I forget. So very, very small set of use cases. We have decided to split up textures and samplers, and don't ever use Bindless for buffers. So all buffers are classic bound. I'm not sure what the opposite of Bindless is. Bindful, maybe. And yeah, texture samplers, I can recommend that. There's other platforms out there where it helps to have it that way. The way we do that, we basically have one set of bound resources on the CPU, and then for each frame, another copy of that. And then whenever we bind a new texture or write a new texture in the slot, then we set a dirty bit, and then update the Vulkan descriptor set for this particular frame when we submit it, just before we submit it. So these are per frame, so we can't change the binding within a GPU frame, right? So we collect all of the binding changes and then submit all of them at once. This is stuff you have to do in Vulkan to get bindless, right? So you alias a lot of bindings. You see the one, so the samplers are on a different slot than the textures. And we actually use Wiki Shader Stage All for descriptor visibility. They never saw any downsides, and I'm actually not sure how to do it differently. So, right. Then on the C++ side of Vulkan, you see there in the visibility Wiki Shader Stage All, basically have the maximum binder texture count and sampler count. You get one descriptor set layout with that, and we have one descriptor set for that per frame, and we have currently 2 frames, right? We have one the CPU is owning, and the other is in the submission. Yeah, I knew there was a slide. So the API is very simple, right? Bind the texture, you can call it whenever in the frame. It just stores that, sets a dirty bit, and then in the submit, we just update the dirty descriptors. Unfortunately, there's no invalid descriptor. I think there's an extension, right, for null descriptors. Okay, never mind. There's always an extension somewhere in Vulkan, so but we don't use that yet. So we set an error texture instead. So if you actually unbind the texture, we set a blinking magenta checkerboard texture, right? Right. All right, then now the fun stuff, synchronization. So as you know, Vulkan gives you more control, but more control means more responsibility. You have to do synchronization yourself. We actually adopted a very explicit, very similar synchronization API in our graphics abstraction layer. So this is code like in the renderer, right, on the topmost thing. And the only thing we did, we basically merged the access flag and the stage mask. So if you're familiar with Vulkan pipeline synchronization, usually you have to specify both, and we merge them into one enum basically with all the combinations we actually use, which is not that many. So that makes it easier to reason about. So Why do we have to do that? We don't have a frame graph, so we have to do that all by hand. So all code there's synchronization is everywhere. And this is okay with validation, because validation on Vulkan is actually good for that. Like, synchronization validation works pretty well to detect missing the validations. The problem is the superfluous, like the synchronization you don't actually need. So this is a bit harder to find out. So it requires some careful engineering and looking at code to do that. Maybe in the future we get a frame graph. Let's see. So one advantage we have with that is that if you have two processes and run on GPU, like the green and the pink one, or whatever, purple one, then you can actually merge these, and it's very visible in the code sometimes. You see lots of barriers, and you have a for loop, and then like a depth pyramid reduction or whatever, and you have multiple of these, then you can merge the passes of these reductions. And it's something you can get with a frame graph, I guess, but it's very hard. Like, you have to support that. All right. There's a helper actually for the texture layer transitions. So 95%, I think, of all textures are very boring. These are loaded up, set in a Bindless texture set, and then never touched again. Like, they never change layout after that. So, and the other 5% we use a helper for that tracks the current layout. So basically, DCD11 style, right? Where you have some CPU current layout internally, and we store that, and we just say what the layout should be, and then it does the appropriate layout transition automatically and batches them up. So we invested our own validation code that sits right beneath or in the graphics API layer. Lots of stuff is validated by Vulkan as well, but the problem is in Vulkan, this code is in a submission code, so you lose a lot of context, because we can validate stuff right in the correct call stack, right? We can say this call here is wrong, and not say something like this command X, Y in the command buffer 13, right? It's a lot further away. And when we started that, we didn't have as many validations in Vulkan. So let's quickly talk about swap chains. It's hard to find any good thing to say about it. To be honest, like especially in Vulkan, it's really, really bad, right? We would love to have some more direct access to DXUI. There's no official way to do that, I think. There's code to do it manually. We don't ship that yet because it looks very scary. And but it would be nice to have some better integration, like an extension for that, meaning all the HER metadata and all the HER control and all of that. Yeah, as all abstractions, Vulkan has its problems. I just want to mention it in general and then have an example of what I mean here. I think that's not Vulkan's fault. I think that's always a problem when you have abstractions and you lose the access to detail, right? And then you maybe for your current problem, you actually need access to detail. So that's a hard thing to do. One example of what I mean here is this tiny little Vulkan command. It's called VK CMD draw index indirect count. Very, very important command if you want to have a GPU-driven pipeline. So it's basically, if you're not familiar, it's basically pointing to a buffer with a list of draw commands you can fill from a computator. So you basically have a computator writing draw commands in the buffer and have another buffer with the count number of these draws. And you, on the CPU side, you say later, submit these, please. So it's a way to spawn work on a GPU. And that's fine. Can anyone tell me why there's a max draw count parameter there? What does that do? Yeah, I saw one hand. If you want to, you can explain it. But yeah, the problem we saw is this max draw count in some architectures actually creates an overhead, and a GPU overhead. So if you call this function with empty buffers, with 0 buffers, so 0 draw calls are generated, and a max draw count of 64K on some unnamed GPU architecture, then it takes 4 milliseconds. Unfortunately, this was key part of our VFX rendering pipeline because we had a lot of very small transparent draws that we sorted and everything. And then we had a 4 millisecond floor performance, but overall that took much less than that. Actual GPU work. We think the problem with that is just the way it's implemented on GPU, and this particular GPU, it has basically, like our mental model is kind of that you have a lot of checks. If the count in the buffer is actually a little smaller than the max draw count, and you have that repeated like 64,000 times. So it's kind of a conditional rendering for us. I'm not actually sure how it's implemented, but it feels that way. So there's definitely some linear scaling involved. One easy way we solve that, we basically have rewritten an index buffer. So we take all the transparent draws, they are sorted already, and we merge all of them into one draw. So it's one draw, and everything was fast. What I say with that, please always measure everything, especially these low-level things, and these have very different GPUs. Like all other GPU architectures we tested that's totally fine. So the max draw count didn't have any influence at all on the performance. All right, conclusions. I really think Vulkan's fantastic step forward. I think I would like to see it used more in the future. I think it's an open standard, and we should embrace that. There's a lot of great tools in infrastructure nowadays, more than 5 years ago when we started. It's nice to see SPV adoption. It's a really, really okay intermediate language. So all of that is great. And we actually shipped Enshrouded using that. There's a couple of downsides though, or things we can improve in the future. So I think a lot of debugging tools would need improvements, right? We have RenderDoc, which is fantastic, but still has no ray tracing extension. So maybe the vendors can sit together and throw a lot of money at Baldur to make that happen. Or someone maybe wants to help with that. And Vulkan has the problem, right? It abstracts over a very large hardware space, or tries to. So we have all this mobile stuff still there. You have to kind of ignore if you want to ship desktop only. But it's possible. All right. Special thanks. We'd like to thank Matthäus and the other organizers for this wonderful conference explicitly. And if you have any questions, fantastic. We actually have an announcement. We sat together and said, okay, is there any company value in this Vulkan backend? And we said, no, it's fine. So we actually ship it on GitHub. So you can take a look. All the 11,000 lines are there. We removed a couple of curse word comments, I think. But everything is there. If you have any questions, if you find a bug, then please file an issue. Would be nice. It's actually used in production. So, and we're actually looking for a junior graphics programmer. So if you understood half of that, then maybe fly. All right, thank you.
All right, so thanks, Julian and Lucas. Do we have any questions? Because we have time for like 2 questions. Oh, there's one question here. And I think Kieran is still preparing his question, right?
So you mentioned you build GPC types on your pipelines, and I was wondering how it was integrating with like building the rest of the stuff and building the game in CPP and stuff. If you have like to rebuild everything for the shader type, if you like, for example, edit it, or like if it's integrated through like a DLL or something.
I'm sorry, I have a really hard time understanding what you're saying. Either you have to speak up or I have to come closer, maybe.
Okay, so the shader type that you build using like the GPC tools, do you have to, when you edit a type, do you have to rebuild the entire games, or is it like integrated inside the game at, I don't know, runtime or something?
What do you mean by type of the shader?
Okay, understood.
Was that
Yeah.
okay?
So when we basically have two separate compile steps for those GPC files. Like one ends up in the asset system that then builds our shader, and the other part is the one that generates C++ code. That's part of our regular code build that builds the exe file. And yet, depending on what you change in the GPC, either you only have to rebuild assets, or only have to rebuild code, or have to build both. And well, with rebuild, I mean obviously incremental build, so only stuff that's changed, that depends on that change, will be rebuilt.
Thank you.
Yeah.
Thank you very much.
Yeah, okay.
So you build for C++, you build your structs with padding, right?
Yeah.
Is it the same order and is in the file, or are you trying to reduce the padding by resorting the members?
No, we actually have to create it according to the layout rules, which are documented and very complicated. It's much simpler now, I have to say, because we switched over to the so-called DirectX layout, so that's much saner. But the classical Vulkan standard layout is unfortunately pretty complicated. I can recommend, if you try that yourself, what we did is we do we reflect and basically reflect the shader data and see if all the offsets match to our assumptions, basically. So we would get a compile error when the reflect has different offsets for the members than what we think it should be on the user side, because it's easy to get bugs in there. So we don't reorder. Yeah.
All right, then thanks, speaker again,
Yep,
and we are the next session.